Okay, so back to finding our rate laws. Get to the right set of notes. There we go. Okay. We're going to find a pseudo rate law. Okay, so what does that mean? We have two reactants. We are going to swamp the reaction, very, very large quantity of it. So that means this one is excess. And so the rate will depend on the reactant there's less of. Essentially, we're making a limiting reactant. So we can find our activation energy, E sub A, from the rate constant and temperature. And this is using the Arrhenius equation. So what we're going to graph is the natural log of K, the rate constant, over 1 over temperature in capital K, Kelvin. So we've got two Ks here, so we've got to be careful with that. We're going to get a graph. And if we take the slope of the graph, multiply it by R, energy R, we're going to get the activation energy. This is what we're going to do in the crystal violet lab and the crystal violet pre-lab. So let's look at this example. Okay, we're not going to do all of these problems. We're just going to answer this one. What is the activation energy? So we have our temperature data and our rate constant. So we need our calculator. So we want to clear all of our lists. Okay. Now we're going to go into Stat and Edit. And in L1, we want to put our temperature. And if this was not already in Kelvin, you would have to convert it to Kelvin, but this is already Kelvin. Okay, so that is list 1. So in list 2, 9.08 times 10 to the 9th. 2.95 times 10 to the 9th. 5.42 times 10 to the 9th. 12.0 times 10 to the 9th. I know that's not proper scientific notation, but those are done a lot of times so that the exponent stays constant so that you can see patterns. The calculator is going to fix it. Okay, so there was our list 2. But remember, what we need to graph is 1 over T and natural log of K. So we want to make a list 3 that does 1 over list 1. And we want to make a list 4 that does the natural log of list 2. So then when we graph, it'll be list 3 as our X and list 4 as our Y. So remember, we want to go up to the top. And so 1 over L1. Oops, forgot the division sign. That's a serious problem. There we go. So there we go. We've got our 1 over Kelvin temperature. And then here, natural log of list 2. And we've got that. So let's make our graph. Second stat plot. And we want to scatter. But remember, we want list 3 to have our X and list 4 to have our y. Okay. We need to if we graph it, my calculator is going to be giving us a line that we don't want. So let's go into our y and delete that. And now let's do our linear regression. Stat calc 4, so linear regression. And we need list 3 as our x, list 4 as our y. We can store our equation in vars, y vars, function, y1, and calculate. Since we turned our diagnostics on the other day, we can check our R value, 0.997. We know that's a good linear fit. We can hit graph and look at our graph. And when we can't see our graph, zoom 9. And look at that. We've got a really nice best fit line. Okay? But remember what we needed. Notes disappeared. All right. Remember what we need is the slope. Okay? So in order to see the slope, quit our graph. And we need to see that linear regression calculation we did. Now on mine, it's right there in the equation. But I don't know. Well, yours should be too. If you click y equals, there's your equation. So there's your slope, negative 1435.7. So we don't need to do the linear regression again. Here are our notes. Okay, so E sub A equals negative R times the slope. So E sub A equals negative 8.3145 joules per Kelvin mole. And we multiply that by the slope, which was negative 1435.7. Okay. And the units for slope, what are the units of slope? We've got natural log over, it's rise over run. Slope would be in Kelvin. So we know it's rise over run. And the rise, natural log, is no unit. And then this is 1 over Kelvin. So we get Kelvin. So Kelvin cancels. And our answer is joules per mole, which is a good unit for energy. So go back to our main screen. So we can do negative 8.3145 times negative 1435.7. And there we go. 11,937. That is our activation energy. Look back at our data, 3 significant digits. So 11900, or 1.19 times 10 to the 4th. Both of those would be in joules per mole, or 11.9 kilojoules per mole. And right here, this is the equation that we were looking at. This is our Arrhenius equation, which looks like our Clausius-Clapeyron equation.